see the video, it actually is already recording what I'm saying, so that's interesting. Okay. Vertical asymptotes versus holes in the graph. G of x equals x squared plus 3x plus 2 divided by x plus 1. So g of x equals x squared plus 3x plus 2 over x plus 1. Let's go ahead and factor the numerator. It's a quadratic. So the factors of 2 that add up to 3 are 2 and 1. So if I look at this right here, I've got, well, first let's talk about denominator. Where does the denominator equal 0? It equals 0 at negative 1. Is it a vertical asymptote or is it a hole in the graph? The fact that it's a common factor in the numerator and denominator an equal number of times, so it's 1 and there's just one of them down here, means that this is a hole in the graph. Now, if you're describing to me that there's a hole in the graph, you can't just tell me that it's at x equals negative 1. You need to tell me the actual location, because that's going to be important for understanding limits. If x plus 1 is a common factor, that means that this function is unaffected by both of these factors, except for at the moment x equals negative 1, which means I might as well just be graphing the graph x plus 2. So let's explore that. If I were to plug in 1, 2, 3, 1, 2, 3, 1, 2, 3, that was not even at all, oh my goodness. Whatever. That's terrible. I'm fired. Okay. If I were to plug in, let's go with something around negative 1. Let's plug in 0. If I were to plug in 0, I would get 0 plus 2. So I would get 2 times 1 divided by 1, right? Those two obviously would simplify each other out, but it doesn't matter. They're 1 right here, but you get 2. So at 0, we'd be at 2. At 1, we'd have 3 times 2 divided by 2. So I'm just plugging in 1 for each of these, right? The 2's cancel each other out. I'm left with 3. So at 1, we're at 3. At negative 2, I'd get 0 times negative 1 divided by negative 1. So I'd get 0 divided by negative 1. That's 0. And at negative 3, I would get negative 1. I know this because I've got a linear function, x plus 2. For all intents and purposes, this is what this graph looks like, x plus 2, except at negative 1. And so what you do is you simplify it out and then you plug negative 1 into what's left over. Negative 1 plus 2 is 1. And so the hole in the graph is at the coordinate point negative 1, 1. And we can see that by thinking, okay, we got a y-intercept of 2, a slope of up 1 over 1, or down 1 over 1. And so we have this hole in the graph right there. And there's our function. So holes in the graph are actually kind of interesting as far as limits go. So let's talk about that. If I were to take the limit of this function as I approach the hole in the graph negative 1 from the right-hand side, so if I approach it from the right, if I approach negative 1 from the right, the function is getting closer and closer to the y value 1. So g of x is approaching 1. Even though it doesn't equal it, it's approaching it, right? And the limit as x approaches negative 1 from the left, so if you approach negative 1 from the left, the function is getting closer to 1 as well. Well, in fact, if the left-hand limit and the right-hand limit of an x value are the same, then you can just say the limit as x approaches 1 is 1. Okay? So that's kind of interesting. Because they're both approaching the same thing, you don't have to identify from the left or from the right. You can just say as it approaches 1, because both sides approach the same thing. That's actually a beginning calculus concept, so there we go. Okay, the only time the denominator equals 0 is at negative 1, and it's a hole in the graph, which means there are no vertical asymptotes. But I want to pose the question, what if it had been opposite? What if we'd had x plus 1 divided by x plus 2 times x plus 1? Then what would we have had? We would still have a hole at x equals negative 1. But all of a sudden the y value would change. And we would also have a denominator, an issue in the denominator at x equals negative 2. Because it's only in the denominator, it's not in the numerator as well, that would have to be a vertical asymptote at x equals negative 2. So then the question is, what am I left with? Where is the hole in the graph, right? So like I said, we simplify those out. I'm left with something divided by itself is 1. So I'm left with the expression 1 over x plus 2. So this function right here would look like this function right here, which is just the reciprocal function shifted to the left 2, right? So we're talking vertical asymptote at -2. The normal reciprocal function looks like this, right? Vertical, horizontal looks like this and looks like this. The more we use this, the more you'll remember that. And so it would look like this and looks like this, except for at -1, there's going to be a hole in the graph. So where is it? Well, like I said, once you simplify out what the common factor is, then you plug in the x value. So -1 plus 2 is 1, so that would be at -1, 1. So it would be your basic rational function shifted to the left 2, but with a little hole in the graph. So we'd have a horizontal and a vertical, and there we go. Okay? So, if the factors in the numerator and denominator an equal number of times, then it's a hole in the graph. If it's only in the denominator or in the denominator more, then it's a vertical asymptote. Let's talk about this one. The only time the denominator in this one equals 0 is at -1. It is not a common factor with the numerator. Therefore, that is a vertical asymptote. Okay? So you might be asking yourself, like, well, what is 4? Like the denominator or the numerator equals 0 at 4, so what is that? So that is something called the x-intercept. When the numerator equals 0, so if I were to plug in 4, I would get 0 divided by 5, right? That's 0. That means that this graph right here would cross the x-axis at 4, 0. So it's just an x-intercept. So an x-intercept is when the numerator and only the numerator equals 0. So that's important. It's like vertical asymptote, denominator and only the denominator, numerator and only the numerator. And we'll talk more about x-intercepts in a little bit. But if I were to go back and think about x-intercepts here, it makes sense that if I think about, like, there's the common factor and it's gone, right? So where does the numerator equal 0? At -2 and at -1. Where does the numerator and only the numerator equal 0? Well, that's the shared factor, so only at -2, and that was my x-intercept. Okay? This, the numerator equaled 0 at 0, but it was a shared factor in the numerator and denominator. So the numerator, other than the 0, never equals 0, which is why it never had an x-intercept. And then this one as well. The numerator 3 can never equal 0, so it can never cross the x-axis. Okay. So let's look at this one. Find all discontinuities and state the type of each. So write down f of x equals x minus 3 over x squared minus 5x plus 6. The first thing we want to do is factor x minus 3. We've got x, the factors of 6 that add up to -5, -3, and -2. This right here and this right here both equals 0 when x equals 3 and when x equals 2. So the question is, what are they? Well, x minus 3 is a common factor in numerator and denominator. Leave me with a 1 in the numerator. And please do not put an equal sign. I'm going to write this out to the side, but these do not equal each other, okay? They do equal each other for all values except 3, which is why I don't want to say that this equals that, because that would disregard the fact that we have a hole in the graph. But the reason why I write this out to the side is so that we can just focus on this for a second. The hole in the graph is at the coordinate point 3, comma. Well, if this wasn't there, then it would just look like this. So if I plug in 3, because remember, this only affects the very infinitesimal moment, 3, x equals 3. 3 minus 2 is 1, so it would be at the coordinate point 3, 1. Where is this right here? If it's a factor in the denominator and only the denominator, then it would be a vertical asymptote at x equals 2. Okay? So find all discontinuities and state the type of each. We've got a hole in the graph at 3, 1, and we've got a vertical asymptote at x equals 2. If I wanted to describe even more so. I would say that this is a infinite discontinuity, and that this is removable. Okay. Um, let's see. I can't really see how long the video is right now. I guess I'll do one more. Yeah, before I start another one. Okay. Find the domain. So domain is everywhere that the function exists. So let's find out where it doesn't exist. The denominator, I don't have to factor it, but it is kind of nice to think of it as 2 times x plus 3. So I've got 5 divided by 2 times x plus 3. The denominator equals 0 at x equals negative 3. It is not a common factor in the numerator and denominator, so I would say that it is a vertical asymptote. And so my domain would be negative infinity to negative 3, negative 3 to infinity, or all real numbers x not equal to negative 3. Let's talk about g of x. So write down g of x equals 3x minus 4 over 3x squared plus 2x minus 8. We're going to factor the denominator. We're looking for factors of negative 24 that add up to 2. So positive 6, negative 4, x plus 6, x minus 4, divide by 3, the leading coefficient. And I get x plus 2. And we get, bottoms up, 3x minus 4. So g of x is actually this function right here in factored form. The denominator equals 0 at negative 2 and at 4/3. Let's look at this. At negative 2, only the denominator equals 0, so that would have to be a vertical asymptote. Whereas this one, it's a shared factor in the numerator and denominator. So if I simplify it out and it leaves me with a 1, then I can think of it as 1 over x plus 2. And I need to figure out where the hole in the graph is, right? So the hole is at the coordinate point 4/3, comma, what? So I'm going to take 4/3 and plug it into this right here. So 1 over 4/3 plus 2. 2 is the same thing as 6/3, or you can think common denominator multiplied by 3 on top and bottom. 6/3 plus 4/3 is 10/3. 1 divided by 10/3 multiplied by the reciprocal, 3/10 is 3/10. And so the hole in the graph is at 4/3, 3/10, and there's a vertical asymptote at x equals negative 2. So the domain would be all real numbers x not equal to negative 2 and 4/3. Dang it, I did that last time. Or negative infinity, negative 2, negative 2 to 4/3, and 4/3 to infinity. So as far as like finding domain, did I need to go through all this? No, but it's unlikely that I'm just going to ask you for domain and not ask you to tell me what type of discontinuities there are as well. Okay, we'll pick it back up in a second.